In this video, I want to talk about vectors and in particular how vectors are connected to linear systems, what we've been working with up to this point in the course. As a starting point, if you haven't already, watch the 3 blue, 1 brown video about vectors. It's a great video and it will give you the necessary background to understand what I'm talking about. In that video, the focus is entirely on vectors in 2 and 3 dimensions, which makes sense. That's where you want to start, and that's where you can visualize things really well. But we'll see that for our purposes, lots of problems, we want to think of vectors in higher dimensions. And that's where I want to start talking. I want to look at what does it even mean to have a vector in higher dimensions? We'll see that we can think of them as lists of numbers, which is probably the most natural way to think about them, but also that we can think of them as arrows in some sense. Now, once we have this notion of vectors in higher dimensions, we can talk about how this all connects to linear systems. And what we'll see is that we can rewrite our solution sets in terms of vectors. We can rewrite the entire linear systems in terms of vectors. And most importantly, this isn't just some academic exercise. It's not just, oh yeah, we can do this. What we'll see is that thinking of linear systems in terms of vectors instead of thinking of them in terms of collections of equations will actually be incredibly powerful. All right, so let's go to vectors in higher dimensions. And I'll just start with 4 dimensions. What would it mean to have a vector in 4 dimensions? Well, one example in that video, the 3 blue, 1 brown video, was that we might want to represent a home as a vector, where the vector has the home's price and its square footage. But a vector, so a 4D vector, maybe we want other numbers associated with the home. So it could represent a home in the following way. A 4-dimensional vector could tell us the home's price, the home's square footage, but it could also tell us the home's age, right? How old it was, when it was built, and maybe the lot size. Right? So it'd be reasonable to want to associate 4 values with a home if we were trying to understand how they were related to each other. So a 4D vector could represent a home. And so maybe for this particular vector, we would have something like, I don't know, the home's price is like $400,000, and the square footage, I'm not sure what market this home is supposed to be and whether these numbers make any sense. Maybe the square footage is 2,500 square feet. The age is 30 years. And the lot size is 8,000 square feet. That might be a vector representing a home. So this is just to say that going up to 4 dimensions makes sense. We have this physics perspective often where we're thinking of vectors as representing actual objects in 3-dimensional space, but vectors show up in all sorts of contexts where the entries to the vectors are not meant to be coordinates in space. So it makes sense to have 4D vectors, to have 10-dimensional vectors. A lot of AI software is using 10,000 dimensional vectors. Vectors in higher dimensions make sense as lists of numbers. And when we think of them as lists of numbers, we can add and multiply them in the exact same way that we do with 2 and 3-dimensional vectors. And that's coordinate-wise. So I'm presenting this in 4D because that's what I want to do, but everything I'm saying applies to higher dimensions as well. So if I have a 4-dimensional vector and I want to add it to another 4-dimensional vector, what that's going to mean is that I add it coordinate by coordinate. So 3 plus 5 is 8, -1 plus 8 is 7, 0 plus 3 is 3, and 1 plus 2 is 3. And similarly, scalar multiplication is going to work in the exact same way. So if I take a vector and I multiply it by some sort of constant, what that means is that I want to do this coordinate-wise. I'm going to multiply each term. 4 times -1 is -4. 4 times -2 is -8, and so forth. So addition and scalar multiplication are going to work exactly the same as they worked in lower dimensions. And again, I'm showing this in 4 dimensions, true up to whatever number of dimensions you want. Okay, so that's numbers. It makes sense to do lists of numbers. We have addition, we have scalar multiplication. What about arrows? Because a lot of that 3 Blue 1 Round video worked with arrows, and visualizing vectors is incredibly useful. So can we do that in higher dimensions? And the answer is kind of. So I'm not gonna, I think I've said this in other videos, I'm not gonna like blow your mind by showing you some crazy 4-dimensional pictures, but I wanna look at 3 dimensions. So here's a picture of some vectors in 3 dimensions, right? I'm not sure what they are. This is just the way Desmos draws vectors. I forget even what the numbers are, but that's not the point. And I want to understand how we could visualize higher dimensional vectors in lower dimensions by saying, look, here's some 3-dimensional vectors here. How could we visualize these in 2 dimensions? And what I don't mean is that, hey, this picture is on a flat screen, right? That's not what I'm saying, because this picture is on a flat screen, right? You're watching this on a computer screen or a phone screen, but you still have this kind of visual perspective where you can understand how this is representing 3 dimensions. I mean, how could we squish these things down into 2 dimensions? Like, for instance, we could do this. So what I've done here is I've taken a perspective on the vectors such that the y-axis is gone. But I can still see these things as vectors in 2 dimensions. Or similarly, I could take a perspective such that the x-axis is gone. And I could think of these things as vectors in 2 dimensions. I just zoomed in for some reason. That wasn't what I wanted to do. And I could get rid of another axis. And we always have to be careful with this. There are risks here. For instance, this blue and this, it's kind of hard to see. Well, this blue, but from this perspective, we can kind of see it. Let's get rid of the purple one. If we're just looking at the blue and the red, these are actually perpendicular in 3 dimensions. But then when I, for instance, get rid of the x-axis, these no longer appear to be perpendicular, right? When I get rid of the y-axis, they actually kind of look like they're in the same direction. So what's the point here? The point is that we can think of higher dimensional vectors in 5, 6, 100 dimensions, and visualize them by just pretending that they're vectors in 3D. Right? So this picture could be a picture that's representing 3 vectors in 100 dimensions. And I'm just thinking of them as vectors in 3D. And this actually is really useful. Well, it'll come up again and again. It can really give you some nice intuition, but you always have to be careful, right? You have to remind yourself, look, just as in the example with the blue and the red, just because these vectors looked like they were in the same direction, right here from this angle, it looks like the blue and red vector are going the same way when I visualize them in lower dimensions. Actually, they're perpendicular. And more generally, we want to be skeptical of our intuition. We want to get intuition by thinking of these things as arrows in lower dimensions, but not just assume that it's true. All right, so I want to introduce a little bit of terminology. Because as we're talking about more dimensions, I want some notation for this. And so just some quick notation / terminology. So if I draw an R, but with 2 vertical lines, this is the set of real numbers. This is a pretty common symbol for the set of real numbers. This is what's known as Math Blackboard Bold. I'm not sure why that's what it's called, but you'll see a lot of these if you take enough math classes, this sort of notation. So R is the set of real numbers, and as we start getting higher dimensional spaces, we're going to use exponents to represent this. So R2 is the xy plane. It's 2-dimensional space. R3 is 3-dimensional space. And R100 is the set of vectors with 100 entries. And now when we want to refer to just arbitrary space where we don't want to specify the number, we'll often write just Rn. So r to the n, saying n is some positive number. All right, so this is just notation that allows us to talk and write about higher dimensional spaces in a nice, concise way. The second thing I wanted to do was connect vectors to linear systems. And in order to do that, I want to go back to some of the examples actually from the week 1 video, just because there were more examples there where I talked about solving linear systems. So I'll show you what the equations are and I'll connect it all. But let's quickly go back. Here was one of the systems that we studied in week 1. And we found that the solution set was the following. And I'm writing them vertically on top of each other for a reason. I'm just going to kind of organize this. So this was our solution set. And again, I'm just organizing variables together and constant terms together. And it turns out I can write this as a vector equation. So the first thing I'll do is highly unimpressive, writing it as a vector equation. The first thing that I want to do is just rewrite this as a vector in R5, in 5 dimensions. And I'm going to do that again in a very unimpressive way. I'm just going to draw in some brackets. So I'm going to think of this as not 5 separate equations. I'm going to think of it as one equation. Let's give myself a little bit of space. Saying that these 2 vectors in 5 dimensions are equal. This system, or this solution set, is equivalent to this vector equation. All right, so this is, I don't think that impressive. But what you can do is you can split everything apart using scalar multiplication. And I can say, look, actually, if I look at the constant terms, I can pull those out. And if I look at the terms with an S, I can pull those out. And if I look at the terms with a T, I can pull those out as well. And so now what I've done is I've rewritten this solution set that previously expressed relationships between what these variables had to be depending on values of S and T. And now I'm saying, actually, this is really saying that if we think of our solutions as vectors, we start with some vector in R5, and then we add some multiples of this one vector in R5, and then we add other multiples of this other vector in R5. And this is going to be a really useful thing, thinking of these solutions as vector equations. And if we go back to the original system, we can actually do the same thing with the whole system. Or maybe not the same thing, but a similar system, or a similar thing, where I'll paste this down here, and I'm going to rewrite this whole system first in a kind of meaningless way. Right, where I just throw brackets on everything and say, hey, this is a relationship in R3. And then I say, hey, let's split apart this left-hand side. That was a plus there, sorry. So here what I'm doing is I'm thinking of each of these variables now as the coefficients on a single vector equation. So I can rewrite my equation itself in terms of vectors. And I think that even without any justification, at least to me, maybe it's the mathematician in me, this already looks really nice. Just the fact that I've rephrased these systems of equations in terms of vectors. But if you're skeptical of why this should be useful, that's totally reasonable. And in fact, it's a good thing to be skeptical of this sort of thing. You know, just because you can do something doesn't mean you should do something. And why should we actually do this? Well, like, why does it make sense to rewrite these things as vectors? Well, see that it's incredibly powerful to think of linear systems in terms of vector equations. One example we'll see is linear regression. So in linear regression, what we're trying to do is we're trying to fit a line or maybe a more complicated equation for more general regression to a bunch of points, but we can't actually make it work. So in other words, we have a linear system that doesn't have any solution. And we want to, our goal is to try to come up with some sort of line that's kind of the best fit possible. Now, if we think of this just in terms of linear equations, it can be hard to figure out how to come up with a solution, but it turns out that once we rewrite everything as vector equations, there's a very natural way to come up with what we call a line of best fit. So something that's not a solution, but that's as good as possible. We'll also just see that we get this computational power out of this. We're going to soon introduce this notion of a matrix, and working with linear equations that look like this, linear systems, is much harder to implement in computers than it is to think of things in terms of vectors and matrices, organized structures of numbers. Hopefully that there's some sense in that, right? That oh yeah, like if we have some more organization to to what we're working with, a computer will be able to handle this better. We'll be able to apply powerful ideas a little bit better. And the reality is that what I've said so far is only some of the reasons to think about vectors in higher dimensions. Right here we have 5-dimensional vectors, and to think about linear equations and linear systems in terms of vectors. In some sense, this entire course is going to consist of a justification of why is this a powerful way to think about things? What sort of problems can we solve by thinking of things in terms of vectors? And what can we do with that? And we're only scratching the surface. You can go much deeper into this. And it turns out that thinking about things in terms of higher dimensional vectors and just generally in terms of vectors gives you a lot of power into solving lots of problems from various areas of mathematics and in other sciences.